What if a single system could provide water storage for household use, fire protection reserves, landscape irrigation capacity, and substantial thermal mass for passive cooling and heating, all integrated into a single straightforward installation that pays back within years through reduced utility costs? That's exactly what strategically located rainwater cisterns accomplish when designed to serve thermal functions alongside their primary water storage role. A typical 5,000 to 10,000 gallon cistern positioned within or against conditioned living spaces provides 40,000 to 80,000 pounds of thermal mass capable of stabilizing indoor temperatures across daily and seasonal cycles. The stored water absorbs excess heat during warm periods and releases that heat during cool periods, reducing heating and cooling loads by 30 to 50% depending on specific configurations and climate conditions. The cistern simultaneously provides water storage that reduces municipal water consumption, supports landscape irrigation without utility costs, and offers emergency water reserves for various contingencies. The integrated functionality captures multiple benefits from a single infrastructure investment, with thermal performance benefits that cistern owners often discover as pleasant surprises beyond the expected water storage advantages. Understanding how cistern thermal mass works, how to design installations for thermal performance, and what benefits homeowners can realistically expect helps capture substantial energy savings alongside the direct water supply benefits. The physics of water's thermal mass performance makes it particularly effective for building temperature stabilization. Water has a specific heat capacity of 1 BTU per pound per degree Fahrenheit, meaning each pound of water absorbs 1 BTU of heat for each degree of temperature rise. Compared to other common thermal mass materials, water's heat capacity is roughly 5 times that of concrete, 6 times that of rock, and 4 times that of brick by weight. The volumetric performance accounting for density still shows water as substantially superior to solid materials for thermal storage applications. A 5,000-gallon cistern, holding roughly 41,700 pounds of water, can absorb 208,000 BTU for each 5-degree temperature rise, representing cooling capacity equivalent to significant air conditioner operation time. The integration of cisterns with building thermal performance requires positioning storage where it can exchange heat with conditioned spaces. Traditional approaches include basement cisterns that absorb heat from floor above and ceiling below, attached greenhouse cisterns that serve as thermal mass for solar heat storage, and sunroom cisterns that stabilize temperatures in those transitional spaces. More sophisticated designs include cisterns integrated with radiant floor systems that circulate stored water through heating and cooling loops, and cisterns positioned within thermal masses like bermed earth walls that coordinate with whole building passive heating and cooling strategies. The cistern construction materials and configurations affect both water storage performance and thermal contribution. Concrete cisterns provide substantial additional thermal mass beyond the water itself, with cistern walls contributing another 20 to 40% to total thermal storage capacity. Polyethylene tanks provide adequate water storage with minimal additional thermal contribution beyond the water they contain. Metal tanks offer moderate additional contribution. The material choice affects initial cost, installation complexity, longevity, and thermal performance in ways that homeowners must evaluate based on specific priorities and site conditions. Felix Marchetti, a sustainable building designer operating across the American Southwest, has documented thermal performance from cistern installations at over 200 residential projects over 2 decades. His tracked projects demonstrate that properly sized and positioned cisterns reduce annual cooling energy consumption by 25 to 45% in hot climates, with similar heating energy reductions in cool climates where stored solar heat serves as an energy source. The specific performance varies with cistern size, positioning, climate conditions, and building envelope characteristics, but consistent substantial benefits appear across the diverse installations. The projects demonstrate that combining water storage and thermal mass functions produces performance that standalone systems cannot match. The sizing considerations for cistern thermal mass involve balancing water storage needs, thermal mass requirements, available space, and budget constraints. Water storage sizing typically aims for 30 to 180 days of household water supply depending on application, ranging from 3,000 to 15,000 gallons for typical households. Thermal mass sizing depends on the building volume being served, with recommendations of 1 gallon of water per square foot of floor area, providing substantial thermal stabilization. The intersection of these requirements often produces optimal cistern sizes of 5,000 to 10,000 gallons for typical residential applications, with this range serving both water storage and thermal mass functions effectively. Isabella Martinez Ruiz, an architectural consultant specializing in integrated water and thermal systems across California, has tracked the economic performance of cistern installations over 25 years of practice. Her client cost-benefit analyses show that integrated cistern systems producing both water and thermal services achieve payback periods of 6 to 12 years through combined utility savings, with continuing returns accumulating across cistern operational lifespans of 50 or more years. The dual-function economics substantially outperform single-purpose alternatives, with thermal performance benefits essentially provided free alongside the expected water storage returns. The tracked performance validates the integrated approach for appropriate applications. The seasonal performance patterns of cistern thermal mass involve different operational modes for heating and cooling seasons. During cooling seasons, stored water absorbs excess heat from surrounding spaces, providing cooling effect without active mechanical equipment. Morning cistern temperatures below ambient conditions create heat absorption capacity that moderates daytime temperature rises. Evening and nighttime cooling cycles transfer absorbed heat back to cooler ambient conditions, restoring the cistern to its heat absorption capacity. During heating seasons, warm solar heat collected by passive solar systems or active circulation loops transfers to cistern water, storing warmth that releases gradually during cool periods. The seasonal function changes require design attention to ensure appropriate heat exchange in both directions. Gregor Nylund, a Scandinavian building scientist who has researched integrated water thermal systems for cold climate applications, has demonstrated that cistern thermal mass functions effectively in heating-dominated climates through proper integration with solar heating systems. His research installations store collected solar heat in large water tanks, providing 3 to 7 days of space heating across winter conditions. The stored heat enables heating strategies that work effectively during cloudy periods when direct solar gains would be insufficient. The applications extend cistern benefits from their southwest origins to northern climates through appropriate design adaptation, and the installation approaches for cistern thermal mass systems vary based on building configuration, site conditions, and homeowner priorities. New construction projects can integrate cisterns into foundation design with optimal thermal coupling to living spaces. Retrofit projects typically involve exterior cistern installations with thermal coupling through adjacent walls or ducted air circulation. Partial retrofits can add cisterns to greenhouse or sunroom additions that integrate thermal storage with new building components. Each approach involves trade-offs between installation complexity, cost, thermal performance, and aesthetic considerations that homeowners evaluate based on specific circumstances. Now for the obstacles and limitations that affect cistern thermal mass applications. First, the substantial space requirements for meaningful cistern installations limit applications to properties with adequate available space. A 10,000-gallon cistern occupies approximately 1,400 cubic feet of volume, equivalent to a room measuring roughly 12 by 12 by 10 feet. Finding appropriate installation locations on existing properties can be challenging, particularly in dense urban environments with limited available space. New construction projects can accommodate cisterns through initial design, but retrofit applications may face substantial site constraints. Second, the structural loading from substantial water weight requires adequate foundation capacity in cistern locations. A 10,000-gallon cistern weighs approximately 83,000 pounds when full, requiring substantial foundation support. Basement installations need floor assemblies capable of supporting these loads, while exterior installations need appropriate footings. The structural requirements add cost and complexity to cistern projects beyond the basic container costs, particularly for retrofit applications where existing structures may need reinforcement. Third, the regulatory approval complexities for rainwater collection and storage vary substantially across jurisdictions. Some regions encourage rainwater harvesting through incentives and streamlined permitting, while others impose substantial restrictions or outright prohibitions. Understanding local regulations before project planning prevents costly surprises and ensures compliance. The regulatory landscape continues evolving, with gradual trends toward acceptance in most regions, but significant variation persists. Fourth, the water quality management for stored rainwater affects operational requirements. Proper first flush diversion removes initial rainfall that carries roof contaminants, while filtration, UV treatment, or other purification maintains water quality for various uses. The management practices add ongoing operational attention beyond simple water storage concerns. Installations without proper management can experience water quality problems that reduce utility and create health concerns. Fifth, the freeze protection requirements in cold climates affect system design. Above-ground cisterns or cistern plumbing must be protected from freezing that could damage containers and piping. Insulation, heat tracing, or installation below frost lines all represent possible approaches with varying cost and complexity implications. The protection requirements add cost and complexity to installations in regions with significant freezing weather. Despite these challenges, cistern thermal mass systems offer substantial benefits for households able to accommodate their requirements. The combined water storage and thermal performance capture multiple utility services from single infrastructure investments, producing favorable economics that single-purpose systems cannot match. Amelia Wright Thompson, a residential water systems contractor operating in the Texas Hill Country, has specialized in integrated cistern installations for 2 decades. Her practice documents that clients consistently report comfort improvements that exceed their initial expectations for thermal performance. The stable indoor temperatures through summer heat waves eliminate the extreme conditions that conventional air conditioning cannot fully address. The reduced reliance on utility water service provides peace of mind during supply disruptions that occasionally affect municipal systems. The integration of multiple functions into single installations appeals to clients interested in resilient, self-sufficient property operation. The practice patterns demonstrate that cistern systems attract increasing interest as awareness of their multiple benefits spreads. The specific design configurations for residential cistern thermal mass systems reveal options that serve different applications effectively. The basement integrated configuration positions cisterns within building foundations where thermal exchange occurs, through the floor above and walls around the cistern. This approach provides substantial thermal coupling with living spaces while utilizing basement space that might otherwise serve limited purposes. The exposed interior configuration positions cisterns within sunrooms or greenhouse additions. where they serve as visible thermal mass alongside passive solar heating functions. The exterior wall configuration positions cisterns against building walls where thermal exchange occurs through shared wall assemblies, capturing some thermal benefit while preserving interior space for other uses. Theodoros Konstantinides, a mechanical engineer who has designed integrated water thermal systems for Mediterranean climate applications, has published research quantifying the specific thermal contributions from different cistern configurations. His analysis shows that basement-integrated cisterns provide the greatest thermal coupling with living spaces, producing 35 to 55% load reduction compared to similar homes without thermal mass integration. Exposed interior cisterns produce 25 to 45% reductions through direct thermal coupling with occupied spaces. Exterior wall configurations produce 15 to 30% reductions through shared wall thermal coupling. The quantitative research helps homeowners and designers choose configurations appropriate for specific circumstances and performance goals. The interaction between cistern thermal mass and other passive design strategies produces compounding benefits that exceed what individual measures achieve. Cisterns combined with properly sized roof overhangs providing summer shade reduce cooling loads dramatically, while cisterns alone cannot. Cisterns combined with cross-ventilation designs leverage evening cool air to restore thermal capacity for next-day heat absorption. Cisterns combined with operable windows and thermal chimneys create integrated passive cooling systems that function reliably without active equipment. The system approach to passive design produces comfort and efficiency outcomes that isolated measures cannot match, with cistern thermal mass serving as a key component in comprehensive strategies. Raquel Santos Jimenez, a sustainable design educator teaching integrated systems approaches at an architecture school in Portugal, has documented how traditional Mediterranean buildings historically used water features for thermal regulation in ways that contemporary cistern applications continue. Her research shows that courtyard fountains, decorative pools, and cistern systems provided thermal regulation alongside water storage and aesthetic functions in buildings across centuries. The historical patterns inform contemporary design decisions about how water features can contribute to building thermal performance in ways that transcend purely decorative or utility functions. The historical precedents validate contemporary interest in integrated water thermal systems as continuations of proven design traditions. The environmental implications of widespread cistern adoption extend beyond individual household benefits. Reduced municipal water consumption eases stress on water supply infrastructure and sources. Reduced stormwater runoff eases pressure on drainage systems and reduces water quality impacts on natural waterways. Reduced energy consumption for heating and cooling reduces associated environmental impacts. The combined environmental benefits compound across populations of households adopting integrated cistern systems, producing meaningful regional environmental improvements through individually modest interventions. The historical precedents for cistern-based thermal regulation extend across multiple ancient civilizations that developed sophisticated water storage integrated with building thermal performance. Roman villas across the Mediterranean incorporated substantial cistern systems that provided water storage while contributing to cooling through evaporative effects and thermal mass. Persian architecture developed qanat cistern systems that captured underground water flows while serving cooling functions for connected buildings. Islamic garden traditions incorporated water features and underground cisterns that provided both cultural and thermal benefits in hot, arid climates. Byzantine construction used large underground cisterns beneath Constantinople's buildings that served water storage alongside thermal stabilization functions. The historical patterns demonstrate that integrated water thermal systems represent long-established architectural traditions rather than contemporary innovations. Dr. Helena Brusati, an architectural historian specializing in ancient water management systems, has documented the engineering sophistication of Roman cistern building connections across multiple archaeological sites. Her research shows that Roman builders understood thermal exchange principles well enough to position cisterns for optimal thermal performance alongside water storage functions. The placement decisions reflected awareness of how stored water would affect surrounding building temperatures, though without the quantitative analysis that modern science provides. The empirical wisdom embedded in ancient construction demonstrates that skilled practitioners developed sophisticated solutions through practical observation and iterative refinement. The research inspires contemporary designers to recognize that traditional architecture embeds valuable thermal engineering insights worth rediscovering. The combining of cistern thermal mass with radiant cooling systems represents an advanced integration approach, producing exceptional performance. The radiant cooling approach circulates water from cool cistern reserves through ceiling or floor radiant loops, absorbing heat from occupied spaces and returning it to the cistern. The cistern stores absorbed heat during daytime cooling operations, then releases that heat through nighttime ventilation or other dissipation mechanisms. The combined system provides highly efficient cooling at low energy consumption levels, with cistern thermal storage enabling radiant cooling strategies that direct active cooling cannot match. The advanced integration demonstrates how cistern thermal mass enables sophisticated building conditioning approaches that would be impractical without adequate thermal storage. The retrofit potential for adding cisterns to existing homes remains substantial when site conditions permit. External cistern installations adjacent to homes provide water storage and modest thermal coupling through shared walls. The installation complexity for retrofits depends primarily on site access for excavation equipment and tank delivery rather than on existing building characteristics. Many homeowners discover that cistern retrofit projects prove more feasible than expected, with installation typically completing within 1 to 3 weeks for typical residential applications. The accessibility of retrofit installations expands the practical applications beyond just new construction to include the broader existing housing stock. Consider what integrated cistern thermal mass systems mean for households able to accommodate them. The substantial water storage reduces utility water consumption, providing both cost savings and independence from municipal supply variations. The thermal mass stabilizes indoor temperatures through daily and seasonal cycles, reducing heating and cooling costs substantially. The fire protection reserves provide defense capability that matters in fire-prone regions. The landscape irrigation capacity supports gardens and grounds without utility water consumption. The emergency water reserves provide peace of mind during supply disruptions. The integrated functionality captures multiple utility services from single infrastructure investments. The dual-purpose economics produce payback periods and lifetime returns that single-purpose alternatives cannot match. The durability of properly constructed cisterns extends benefits across operational lifespans of 50 or more years. The environmental benefits accrue alongside personal advantages at household and community scales. The maintenance characteristics of properly installed cistern systems prove remarkably modest across decades of operation. Annual inspection of filtration components, overflow systems, and connections typically requires an hour or two of homeowner attention. Periodic cistern cleaning removes accumulated sediment every 5 to 10 years, depending on water source quality and pre-filtration effectiveness. Structural inspections every decade verify container integrity. Plumbing maintenance for pumps and distribution systems follows patterns similar to conventional well or plumbing systems. The total maintenance time across decades of cistern operation typically measures in tens of hours, rather than the hundreds of hours required for systems with more active components. The low maintenance burden makes cistern systems attractive for homeowners seeking low upkeep infrastructure alongside the substantial functional benefits. Benjamin Oduya, a water systems engineer who has designed cistern installations for agricultural and residential applications across East Africa, has documented how cistern thermal benefits prove particularly valuable in tropical climates with extreme temperature variations. His installation data shows that cistern thermal mass reduces indoor temperature peaks by 8 to 14 degrees during hot weather, while raising minimums by similar amounts during cool periods. The moderated temperature ranges provide comfort without active cooling equipment in regions where mechanical air conditioning remains expensive or unreliable. The tropical applications demonstrate that cistern thermal benefits extend across diverse climate conditions beyond the temperate contexts most familiar to North American audiences. The approach works for appropriate applications with adequate space, structural capacity, and regulatory compatibility. The psychological benefits reported by cistern owners deserve recognition alongside the quantifiable economic advantages. Homeowners consistently describe feelings of security knowing that water reserves and thermal mass provide buffers against various disruptions that concern them. The independence from municipal systems for portion of their water needs provides peace of mind during events ranging from supply contamination to infrastructure failures. The connection with natural water cycles through rainwater collection creates satisfying relationships between household operation and environmental systems. The visible stored water serves as tangible evidence of self-reliant property management that many owners value beyond its practical functions. These intangible benefits matter to homeowners even when they cannot be expressed in direct economic terms. The question isn't whether integrated cistern systems provide substantial benefits for appropriate applications. The question is why more homeowners haven't explored these integrated approaches that combine multiple essential services into single infrastructure investments. The answers typically involve awareness limitations rather than genuine obstacles to successful implementation. For homeowners interested in self-sufficiency, energy efficiency, and resilient property operation, cistern thermal mass systems represent compelling options worth serious evaluation. The combined functionality, favorable economics, durable construction, and minimal maintenance create infrastructure investments that continue delivering value across decades of property ownership, benefiting multiple generations of occupants while reducing environmental impacts at household and community scales.